Code Explained says hi. Today we're going to see another tutorial about JavaScript. We're going to create a Tetris game using only JavaScript, no framework. Let's now see a preview of the game. Our tutorial, the plan. We're not going directly to type in our code. Instead, we are going to understand everything about the game, understand how things works, understand the code we are going to write, and after that we will go and open our text editors and start typing our codes. To create JavaScript games, we will need the HTML5 element, which is the canvas. We will give it an ID and a width and a height. So in our web page we will get something like this, a canvas with a 200 pixels in the width and a height of 400 pixels without the borders. Then we need to link our HTML5 to a JavaScript and external JavaScript file, Tetris.js, because everything else will be done using JavaScript. The first thing we're gonna do is select our element canvas, then get the context of the canvas, which gives us methods and properties that allow us to draw and do a lot of things on the canvas using JavaScript. One of them is draw a rectangle. To draw a rectangle, we have to give it a color, blue for example, and then we will use the fillRect method. For example, if we say x is 100, means this is 100 pixels from the left. If we see y is 150, then we must take 150 pixels from the top. This is the x and y position of our rectangle. Then if the width is 50, means the width of the rectangle will be 50 pixels. The same for the height. Then our rectangle will be in this particular place or position. Now we may need to add a stroke. The same thing. We define the stroke style, a color, red for example, and then we use stroke correct and we will give it the same arguments as fillRect. In this case we will get a stroke on our rectangle. What we should know about the Tetris game. Here's our canvas, and this is the board or the game board. The game board has 10 columns and 20 rows. By default, we can use any number of rows and columns we want. This is a Tetromino or a Tetris piece. Now you must see here that the game board and the Tetromino are both just made of squares, the same square. Our square here is by default 20 pixels by 20 pixels. The Tetromino can go to the right or to the left or rotate by the player. Also goes down by the player and drop automatically. Now when it reaches the bottom, we have to lock this Tetromino to the board and then call for a random Tetromino again. These are called walls in Tetris. We have a left and a right wall. Draw a square. So as our game board and the Tetromino, the pieces, are made of squares, so we will need a function to draw squares. Here is our board. Let's say we have this square. To draw this square, we may define first the fill style or the color. In this case it's red. Then the fillRect. Remember that our square is 20 pixels by 20 pixels, so any square in the board is 20 pixels width and a height of 20 pixels. Now let's define the x position here. So we have 20 pixels, 40 pixels, then 60 pixels. Then for the x it's 60. For the y position, here is 20 pixels, then 40 pixels. The width or the height are both equal to 20 pixels. We have here a black stroke, and then the stroke correct must get the same arguments as fillRect. Now there is a better way to do this. First, as our square has the width and the height both equal to 20 pixels, we will need to define only one constant, sq equals 20 pixels. As I said, there is a better way to draw a square. Let's say setX fill style equals red, in the red color, then setX.fill rect. The idea here is instead of using pixels, instead of saying 60 pixels, we will go to the left and count the number of squares. We have here 3 squares, so we'll say here 3 squares, or 3 times square. The same thing for the Y position. This is 1, 2, so it is 2 squares. And then for the width and the height, they both equal to square. And here is the code for the stroke. So the idea is instead of using pixels, we use a square. Now our function square here has 3 parameters. X is the number of squares from the left, Y is the number of squares from the top. And then here is our code for the draw square. I have here a small exercise. Let's say we have this square here. What should be the draw square arguments? We will need to go and count the number of squares from the left. 1, 2, 3, 4, 5. So for X it's 5. Then for the Y we have here 1, 2, 3, 4, 5, 6. So it's 6. The color of the square is green, so here must be green. The game board. Our game board has 10 columns and 20 rows. We will need the code to create the board and one to draw the board. We must first set our constants, the row and the column. The number of the rows are 20 and the columns are 10. Now as you can see here, our board has squares with a white color, and whenever there is a square with the white color, we call this an empty square or a vacant square. So we need another constant called vacant, which is equal to white color. Now we defined our board as an empty array, and then we use a for loop to create the rows, and we initiate them with an empty array. Then we create our columns. Then we set every square of the board or every tile to vacant, a white color. Now to draw the board, we will create a function called draw board, and then we will use the same code, the for loop for the rows and for the columns, and then we'll use the draw square. So board with index R and C here is the color, which will be white. Then R is the Y position. Here you have to remember from now on that when we are talking about rows, we are talking about the Y axis. And for C here is the X. The same thing when we are talking about columns, we are talking about the X axis. And then we should call the draw board to draw our board to the canvas. Let's see some examples here. This square here is board with index 0, 0. This one here is board with index 9 and 4. This one is board with index 19, 9. The Tetrominoes or the Tetris pieces. There are 7 Tetris pieces. 5 of them are a 3 by 3 array and 2 of them are 4 by 4 array. Let's say if we give this a color, this square, and this one, and this one, and this one, and we keep all the others vacant, then we just created the Z piece. This is the S1, the J1, the T1, the L1, and this is their axis of rotation. This is the I piece, and this is the O piece, and this is their axis of rotation. This is an example. Let's say we have to create the Z piece. We will say const Z equals an array, and then we have this pattern. The first pattern is this of the piece. When we first rotate the piece, we will get this. When we second rotate it, this, and then this. So we need 4 arrays inside the first array. Now you must know that if a square is vacant, we give the value 0. If it's occupied, we give the value 1. Here's an example for the first pattern. This one is occupied, so we give it 1. This one 2, and this one is vacant, we give it 0. So the first value of the first array will be something like this, 1, 1, 0. Then for the second row, we have 0, 1, 1. For the third row, 0, 0, 0. And the same thing for the other patterns. Let's now talk about how to draw a piece. Let's say we have the Z piece. This is the code for the Z piece. This is Z with index 0, with index 1, 2, and 3. Let's define a variable piece and initiate it with Z with index 0, the first pattern. Then we need a color for our piece, orange in this case. Now, every pattern here has 3 rows, so we need a for loop that starts from 0 and stops on 2. Then we have 3 columns. We need another for loop to loop over the column, or we just have to say piece.length. This will return 3 for both the for loops. You already know that 0 is false and 1 is true. The idea here is that we need to only draw the occupied squares. There is no need to draw the vacant ones. So we will use an if statement. So if piece RC is 1 is true, then we draw the square. Running this code will give us the first pattern in an orange color. This is a code to remember. Object in JS, just things we need. There are different ways to create objects in JS. One of them is using a construction function. Example, we see function, then the name of the construction function. Here are the parameters, and these are the properties and method. Now to create an instance of dog, we use the new keyword. Example, let max equal new, then dog, the construction function, and then the argument. We can create a lot of instances of dog this way. Now the problem here is, let's say we need to show profile of every dog using this template, and then we have a very long list. So this will be hard to go over them all one by one to show the profiles. So what is the solution? The solution here is prototype. What is prototype? Prototype is just an object. An object has properties and methods. Let's say function here. Function here in JavaScript is an object, means this function has properties and methods. Now when we created the construction function dog using function, and somehow dog has inherited all the properties and methods of this function. Means dog can access those properties and methods. Same here, when we created Max and Rocky and Lucy, these instances here can also access the properties and methods of dog. Means they can access the prototype of dog. So we don't need to go and we don't need to go and add a method showProfile to every one of them. We just need to add the showProfile method to the dog's prototype, and then these instances here can access that method as long as they can access the prototype of dog. Now, how to add a property or a method to a prototype of an object. We say the name of the object, dog, dot prototype, then dot the property or the method. ShowProfile here is our method, equals function. Then returns the name is 8 years old, its color is color. Now if we say max.showProfile, Max can access now the showProfile as long as it is in the prototype of dog. So this will return this line, the same for the other instances. Now let's talk about piece, our construction function. So we need to say function, then piece, then the parameters, the Tetromino and its color. To create an instance of piece, we will say let piece equals the new keyword, piece, and here Z is the Tetromino and blue its color. Now the first property is Tetromino, so it's like saying that piece.Tetromino equals this code, the code for the Z Tetromino. Here we define another property, Tetromino number equals 0. You already know that this is Z with index 0, 1, 2, 3. So we set Tetromino number to 0 because we wanted to start from this pattern. The next property is active Tetromino, means the piece or the pattern we are playing with in the real time. So this code here is like saying Z with index 0. Then this dot color should get the blue in this example. Now for our pieces, this is the game board, the top of the board. Our pieces must be in this place by default before they drop down. Here is the X position. So the X position by default of this piece is 1, 2, 3 squares. So we must add another property which is the X position. So we'll say this.x equals 3. And then for the Y position, this is -1, -2. So this.y equals -2. Coordinates of a square. This is the code so far with we draw a piece. And this is our board. Let's say we have a piece in this place. When the first loop runs, this is like saying this is r equals 0, 1, and 2. Then when the full loops runs, it's like saying this is column 0, column 1, and column 2. Now for the X position, this.x equals 3. We have 3 squares from the left, and we have 2 squares from the top, so this.y equals 2. Let's take an example. We have this A square here. What are the A coordinates? So simple. So for the X position, this is 1, 2, 3 squares. So X equals 3. Now for the Y position, here is 1, then 2. So Y equals 2. But how do we calculate this using code? The code is X equals this.x plus the number of the column. Equals 3 plus 0, then equals 3. The same thing we got. For the Y position, we will say this.y plus the number of the row this time. So it's 2 plus 0, then equals 2. Let's see another example, the B coordinates. We'll say x equals this.x plus c equals 3 plus 1 equals 4. Here's 1, 2, 3, 4. So for the x, it is 4. For the Y position, it is 3. Let's check that. So here is 1, 2, 3. The same for the C coordinates. You can check that yourself. So now, in general, any square of the Tetromino, its coordinates, its X position and Y position are given like this. The X position is given by this.x plus the number of the column, and the Y position is given by this.y plus the number of the row. Now we need to move the active Tetromino. Remember, we need to move our pieces right and left and down and rotate them. So let's say we have a piece here, a Z1 with the blue color. Here is our board. The Z piece must have a blue color and must be in this position. Why? Because we already said piece.x equals 3 and piece.y equals -2. Now to move down the piece, we must use the move down function. What does the move down function does is increment the Y position. So simple. We will increment the Y position by 1 square. And then we must draw our piece in the new position. But this code here has a problem, because it will draw another piece under the first one, and so on. So the piece, our piece, must look like it's getting bigger and bigger. So we have to solve this problem. And the solution is, before drawing the new piece, we have first to undraw, or to delete if you want, the first one. Undraw the piece first, then increment the Y position, then draw the piece in its new position. The same thing goes for the move left function. Let's say we have our piece here, and then we want to move our piece to the left. We first need to undraw the piece, like this, and then decrement the X position, because we are going to the left, and then draw the piece in its new position. Same thing goes for the move right. Say we have our piece in this place. We have first to undraw the piece, and then increment the X position, because we are going to the right, and then draw our piece in its new position. Let's talk now about the draw and undraw functions. The idea behind the draw and undraw functions is very simple. When we use the draw function, we draw the piece with its own color. But when we undraw the piece, we draw the piece with white color. Which means draw and the undraw do the same thing, just they use a different color. Draw uses the piece's color and undraw uses white color, the color of a vacant square. The code of the draw function. We must say piece, then dot prototype dot draw. We're adding a new method to the piece construction function. Equals function. We use the first for loop and the second one. And then if the square is occupied, we use the draw square function. Remember, the x position of a square is this dot x plus the number of the column. And its y position is this dot y plus the r, the number of the column. And then we use for draw this dot color. This is the color of the piece. Like we said, for the undraw function here, has the same code. The only difference is this. Instead of using the color of the piece, we will using the white color, the color of a vacant square. Now let's talk about how to control the pieces. To control the pieces, we will use the arrows on our keyboard. You must know that every key on the keyboard has a code. For example, let's talk about the arrow keys. For the left key has a code which is equal to 37, 38, 39, and 40. To know which key is pressed by the player, we need to add an event listener to the document, which is in this case on key down. So now, whenever our player press a key on the keyboard, this function here, control, will fires up. Let's now talk about the control function. The control function gets event as argument, which is key down. Now f, the event dot key code. This is how we get the code of the pressed key. If it's equal to 37, then it's the left arrow. Then we should move our piece to the left. Now else f, the event dot key code is 37, which is up, we have to rotate our piece. Else if it equals to 37, then we have to move our piece to the right. If it's 40, then we have to move the piece down. So simple. This is our board. Now let's say we have a piece here. If we move it to the right, then it will be beyond the right wall. Same here, if we move it to the left, it will be beyond the left wall. The same for this one, and the same if we have a locked piece, and then we have a piece above it. If we move it down, it will go through the locked one. This must not happen in the Tetris game, so we need here a collision detection function. What does this function do is before any movement of a piece, right or left, down or rotation, we have to check if that movement won't lead to a collision. Means check if there will be a collision. If it's false, we do the movement. If it's true, means there is a collision, we don't do the movement. Example, let's say we have our board and then this is the eyepiece. When we move the eyepiece to the right, then the piece will be in this place. Now for the collision detection function, it has to check this one, not this piece, not the actual piece, not the piece we are playing with, but it has to check if there is a collision with the piece after the movement. Same, when we move left the piece, the collision detection function needs to check this piece here. And the same goes for the move down and rotate the piece. So, the detection collision function needs to know the coordinates or the future coordinates of the piece and the piece itself. So we'll say prototype.collision equals function x and y will get us to know the future piece coordinates. And then this is the piece. Now the x and y positions are the value of x and y that the collision detection will get as arguments, they depend on the movement. How? Let's see some examples. If we say we need to move left the I piece, the piece will be in this position. Now, if we see for the y position, it didn't change, so the y position still the same. But for the x position, after we move left the piece, it will decrement by 1. So here, our collision detection function will get x decremented by 1, and then y didn't change, it will be equal to 0. Let's now go and see the example for when we move right the piece. So here is our piece. If we move it right, it will be in this place. Again, for the y position, it won't change. So here, y equals 0. Now, for the x position, it will be incremented by 1. So here, x equals 1. So here, the collision detection function will get these arguments, 1 for x, 0 for y, and the active tetromino for the piece. Let's talk about the last one. We move down the piece. When we move down the piece, it should be in this position. Now it's the opposite. The x position won't change, it will stay the same. So x equals 0. And now for the y position, it will be incremented by 1. So y, it will be equal to 0. So this is the collision. The arguments are 0 for x and 1 for y, and the active tetromino. Let's go now and update our movement functions. Our movement functions are looking so far like this. Now we have to check that there is no movement before any movement. So we'll say f, there is no collision when we move down, else we will do things we will see later. The same for the move left. We need to check if there is no collision when we move the piece to the left. And for the last one, the move right, we need to check if there is no collision when we move right the piece. The collision detection function. We need to check if there is a collision, which means we need to use conditions based on the new x and the new y. The new x and the new y are just the new coordinates of the piece after the movement. What are these conditions? Let's see here our board. We have the right wall, so every piece behind this wall has an x less than 0. This is the right wall. Every piece beyond this wall has an x greater than the column. For here we have a y position less than 0, and here we have a y position greater than a row. Now, to check if there is a collision, we simply check all the Tetromino squares, which means we need 2 for loops for that. And then our if statements. The first if statement, we need to check if the square is vacant. Then we go to the next one. Here is an example. This is a piece, and these are the vacant squares. If we check the vacant squares, so there is a collision in this situation, which is not. So we need to say if the square is not occupied, we skip it, we continue. The next if statement, we check if the squares are beyond the boundaries. So we'll say if, for this piece, we have the new x is less than 0. For this one, or new x is greater than column. For this one here at the bottom, we have the new y is greater than row. Then we return true. There is a collision. Now, if we have a locked piece here, we need to check if our Tetromino squares are not going to go through some occupied squares, like this. So we need to say if the board with the new y and the new x as indexes are not vacant. So we return true. But we have a problem here. Let's say we have a board with index -1, which means the new y is less than 0. This will crash the game, as there is no index with -1. So we have to skip them. So we'll say if the new y is less than 0, continue. Then all these if statements go here. Now let's go and write the code for our collision detection function. So we'll say piece.prototype.collision. Remember the parameters. We will need to use the for loops, so we check all the squares of the Tetromino. And then we have to check if there is a vacant square, and we skip it. Now we define the new x and the new y. Remember, the coordinates of any square of a Tetromino is this, the x position, and this is the y position. Now the coordinates of any square of the Tetromino after a given movement, this that x plus c plus x, the one that collision gets as argument, and then this plus y plus r plus y. Then we check if our piece won't be beyond the boundaries, and then if the new y is less than 0, we skip it, because it will crash the game. And then we check if the board with the new y and the new x is not vacant, means there is no locked piece already in the place. And then if none of these are true, we return false. Let's now see how do we rotate a piece. Let's take an example with the Z piece. This is the code. Now, this is the Z with index 0, the first pattern, the next one, the third, and the last one. This is the first pattern when we rotate it the first time, the second time, and the third time. So to do the rotation, it's very simple. We just have to go from Z with index 0 to Z with index 1 to 2, then to 3, and get back to 0. So simple. But how can we do that in code? Means how can we go from 0 to 1 to 2 to 3 and then go back to 0? If we do that by just incrementing the index, it won't work. So to solve the problem, we will say the first index 0 plus 1, then modulo, we have here at the top 1, 2, 3, 4, 4 parents, so we have to say modulo 4, this will give us 1. When we go to the next parent, we will say 1 plus 1, modulo 4, this will give us 2, and this one 3, and the last one it will give us 0. Now let's see that using code. We already set Tetromino number equals 0. Then when we say this that active Tetromino equals this that Tetromino with index Tetromino number, just like saying Z with index 0, then we draw this to the board. Now we have seen how to increment the Tetromino number. We say Tetromino number equals Tetromino number plus 1 modulo Tetromino that length. So this that Tetromino number equals 0 for now, plus 1 modulo, and this that Tetromino that length will return 4. So this that Tetromino now will equal 1. So this is how we update this that Tetromino number. Now then we have to update the active Tetromino by using the same code as above. This is like saying Z with index 1, and we successfully rotated our piece. Now let's type the code for the rotate function. We'll say piece.prototype.rotate equals function. We need first to undraw the piece. Then after that we have to increment the Tetromino number by 1. Then we update the active Tetromino, and then we draw the new pattern. Now let's say we have our piece in this place. We rotate it, then go to the right wall, and then rotate it again. Our Tetromino will go beyond the right wall, so this is a collision. So now we need to do the same things we did with the move down and right and left movements. We need to check if there is no collision after the rotation, then if not, then we do the rotation. But we have to know some things. When we rotate a piece, it's done in its place, means no movement is done during the rotation, means the coordinates of the piece after the rotation remain the same. If they remain the same, means x will equal 0 and y will equal 0. These are the arguments, the first arguments for our collision function, if you remember. And then, before we rotate the piece, we need to check if the next pattern won't lead to a collision, not the active Tetromino. So, which means the collision function must get the next pattern. So let's now update our function. So we have first to get the next pattern. This is how we increment the Tetromino number. Then we have to check if there is no collision. So here we say 0, x doesn't change, y doesn't change, 0. Then it gets the next pattern. Then we use the same code, this.undraw. We increment the Tetromino number by 1. Then we update our active Tetromino, and then we draw the new pattern. Again, after the last update of our rotate function, we have a problem. Let's say we have a Tetromino next to the right wall or next to the left one. These won't rotate. Why? Because if they rotate, there will be a collision. But in a real Tetris game, they rotate. How? They move to the left and then rotate. For the left one, it moves to the right and then rotate. But here you must know that we don't see the movement. The movement is done in the background. We just see the rotation. So the problem here is solved by what we call the wall kick. So before the rotation, the wall kicks the piece and then the rotation is done. So how do we do that with code? We check if there is a collision after the rotation, then if true means there is a collision, then we have to know in which side the collision happened, means is it the right wall or the left one. Here is the column divided by 2, the middle of the board. Every piece in this place has an x position less than column divided by 2. In this position, every piece has an x greater than the column divided by 2. So we use an if statement. If this.x is greater than column divided by 2, then it's the right wall. Remember, if it's the right wall, we need to kick the piece to the left. Kick it by 1 square, so we will set kick equals -1. Else, if this.x is less than column divided by 2, it means it's the left wall. Here we have to kick the piece to the right, which means kick equals 1. And then, before we do the rotation, we first kick the piece. Now here is the last update for our rotate function. So, the code so far for the rotate function looks like this. Now we have to set a new variable called kick. We set it to 0. And then we check if there is a collision. If true, we need to check in which side the collision happened. If it's the right wall, we set kick to -1. If it's the left wall, we set kick to 1. Then we check if there is no collision with the kick. If there is not, then we have to undo the piece and then kick the piece and then increment our Tetromino number and then update the active Tetromino and then draw the new pattern. Now, when our piece reaches the bottom, we have to call for another piece randomly, so we'll need here a new function called random piece. Before that, we have to set a constant pieces that has all the pieces with their colors. Now our random piece function will generate a random number using math.floor. Math.floor, for example, if we give it 4.5, it will return 4. If we give it, for example, 6.7, it will return 6. Then we'll use math.random that will generate numbers between 0 and 1. So to generate numbers between 0 and 7, we have to multiply it by the pieces that length. The pieces that length here equals 7. So this must give us numbers between 0 and 6. And then we return the new piece. For example, if random number is 1, then we are talking about this value. Then with index 0 is the piece S. Here the pieces with index 1, it's green, it's the color. Now this is the last update for the move down function. So else, if there is a collision, we need to lock our piece, and then we need to generate a random piece. Now this is our board. This square here is vacant. If we say board with index 6, 4, we will get white, the color of a vacant square. Now if we say board with index 6, 4, and then equals red, and then we draw the board again, this will give us this. This is the idea behind how to lock a piece. So locking a piece means change the color of the board squares. Let's say we have a piece here that must be locked. This piece here has a color given by this color, and any of its squares coordinates are given by the x position is given by this x plus the column, and the y position. Then to lock this piece to the board, we just have to change the board squares to that color. So we'll say board equals. We have to change those squares exactly, so we need to say board with this y plus r and this x plus c equals this color. Now let's write down our lock piece function. So we will say here piece prototype lock equals function, and then we need to loop over all the Tetromino squares. Then if there is a vacant square, we have to skip it. We don't want to lock vacant squares to the board. And then we will check if this y plus r is less than 0. This is the y position of the square. Means we have to lock the piece in this place, which means we have a case like this. Remember, the pieces here has a y less than 0. Locking a piece here means a game over. So if this is true, we have to say game over equal true. Then we alert game over for the user, and then we break from the loop. Then we change the board's colors. So this is the square's coordinates, and this is the active piece color. Now let's talk about how to remove a full row. This is a full row. In this case, we must eliminate this row and increment the score. Every time we lock a piece to the board, we have to check if there is a full row. If there is, we have to remove it, which means this code here must be in the lock function. Inside the lock function, we have to loop over all the rows on the board. Every time we lock the piece, we have to loop over all the rows on the board. Means we need to use a full loop. And here we set r less than 0 as a condition, which means we loop over the rows of the board, not the piece. And then we will declare is row full and set it to true. After that, we have to loop over the columns one by one. So we'll use a full loop, and then inside we will say is row full equals is row full, and the board with index RC is not vacant. What does this mean? When we go check the first column, if that square is not vacant, this will become true, and true, this is true. If we go again to the next one, and this is true, then this is true, and this remains true. But if this is false just once, and we have here a logical end, the row is not full. Now if the row is full, then we need to move down all rows above it, like this. which means the first row becomes the second becomes the third becomes the fourth, and so on. So we need here to use a for loop. We start from the row, which is full, until y is greater than 1, and then we increment y by 1. Then we will use another for loop to loop over the columns, and then we say board with index y equals board with index y minus 1. So every row equals the row above it. This is how we move down all the rows. Now you must know that the top row, the board with index 0, has no row above it, so we have to create it again. So we need to use a for loop and set all the columns of the first row equals vacant. And then we have to increment the score by 10. And finally update the board. Drop a piece. In Tetris game, we need to drop the piece every 1 second, which means we have to call the move down function automatically every 1000 milliseconds. So we need here a drop function that calls the piece that moved down automatically. The best way to do that is using the request animation frame. So what happens here, after we call the drop function here just one time, the piece that moved down runs, so the piece moved down, and then the request animation frame here will call drop again whenever our browser is ready. But before we move down the piece, we need to check if it's already 1000 milliseconds. So we have to say if delta is greater than 1000 milliseconds. What is delta? Outside the drop function, we have to set a drop start variable which is equal to date.now. And inside the drop function, we have to set the variable now equals to date.now. And then delta will be equal to now minus drop start. So delta is the difference between the now time and the last time we dropped our piece. Then after we move down the piece, we have to set the drop start to date.now. Now our request animation frame must be called in one condition. If it's not, a game over. When our game starts, we have to set game over to false. Now we have to improve how we control the piece. This is the code with we control the pieces. We don't want to drop the piece when the player takes an action. Means when we rotate the piece or move left the piece or move it right, we don't want the piece to drop down. So what we have to do here is whenever the player takes an action, we have to set drop start to date.now. So when we move left the piece and when we rotate it or move it right, we have to set drop start to date.now. I think you're ready now to type in our code. Are you? Before, if you're not subscribed, please subscribe. If you are, click the bell so you get notified about every new video. Before start, go to the code explained repo on GitHub. The link is in the description. And go select Tetris JavaScript. We have here the full game files if you want to see them. The one we need is Tetris starter template. Go and download the file. Now extract the files. I will open this as a brackets project. The files we have inside are index, Tetris, and the pieces, the code for the pieces, so you won't have to type over all the code. Then in index.html, we'll create the very basic HTML file with the title Tetris game JS, and then inside the body, we'll create our element canvas with an ID Tetris and the width of 200 pixels. And the height of 400 pixels. Then we will link our HTML file with this script Tetrominoes.js and Tetris.js. I will go now and run a live preview of the files, and then open the console. Now, inside Tetris.js, we create the first constant, canvas, selecting our element, canvas, and then get the context of the canvas, now the constant row, which is equal to 20, and column, which is equal to 10. The square size here is 20 pixels by 20, so we'll use just one constant. Then the constant vacant equals white. Remember, this is the color of an empty square. Now let's draw a square to the canvas. We must set first a color, red for example, then use the fill rect, the x position 0, y position, and then the width and the height. I'll change them so our square will look bigger. Then I will need a stroke, so I'll say stroke style, black for the color, and then stroke rect. I will give it the same arguments as fill rect. Now I see here a red square with a stroke with a black stroke. To make this code reusable, we will need a function called draw. The color may change, so we will make this as a parameter. The y position also. And here is the x position. The same for the stroke. Now if we call draw with 0, 0 for x and y and red, we'll get the same results as before. Now our draw square won't use pixels, we will use square as a unit, if you say. Then the width and the height of all squares are the same, so we'll say square for the width and the height. Now let's create the board. The board is an array, a two-dimensional array, so we will use a for loop to create the rows. We set first all the rows as an empty array. Then every square of the board must have a white color for the moment. Now after we created the board, we have to draw the board to the canvas. We will use a function for that called draw board. We'll use the same code, so I'm gonna just copy the code. Then I will use the draw square here function, x and y. So the board with index C is the color, the y position is R, and the x position is C, the number of the column. Then I will call draw board, and now we should see our board drawn to the canvas. Now let's go and create the object piece. So we'll say function piece, our construction function, gets in Tetromino as parameter and its color. We'll say this that Tetromino equals Tetromino, the code for every piece. Then this dot color equals color, the color of every piece. This dot Tetromino number 0, we start from the first pattern. Then this dot active Tetromino means the Tetromino we are playing with equals this dot Tetromino with index this dot Tetromino number. Now we will need to To control the pieces, so we must add some coordinates. This.x equals 0 for now, this.y equals 0. Let's now create the pieces and their colors. I will create a constant called pieces equal an array. We have here 7 pieces, so I will just copy this 7 times. And then I will type in every piece and its color. The Z has a red color, the S you can choose any colors you want, T yellow, and O with a blue color, the L with a purple color, and the last one is the J with an orange color. Now we have to initiate the piece. We will say let p for the piece equals new, the keyword to create an instance of an object. The Tetromino here is pieces with the index 0. So this is the Z piece here, and one, it's red, its color. Now let's go and create the draw function to draw the piece. I will say piece dot prototype dot draw equals function, no parameters. I will use a for loop to loop over the rows, so I'll just go and copy the code. So here we will say this.active Tetromino, that length. I'll just copy the line. Then f, the square, is not empty. We want to draw only the occupied squares. Then draw square. To control the piece, we have to see this.x plus c and this.y plus r. I'll save that. Let's now try p.draw. Now we should see our piece in the canvas. So now to move our piece, we just have to change the coordinates, the x and y. I will set this to 3 and 0 for the y position for now. Then we will need to move down the piece. So say piece.prototype.move down equals function. So we have to increment the y position and then draw the piece in its new position. In Tetris game, the pieces drops automatically every 1 second. So we need a function called drop, function drop. Then this will call the p.move down, and we'll use request animation frame after we call the drop function. Now the code works, but the piece is moving down so fast, so we need to control the time. I will say let drop start equal date.now, and then inside the function I will declare a new variable called now, date.now, and then delta, the difference between now and drop start. Then I will use an if statement here. I will say f delta is greater than 1000. We draw the piece, and then we set drop start to date.now. Now we should see the pieces dropping down every 1 second, but the problem here is our pieces is getting bigger, so we have to undraw the previous piece or the last piece. So I have to set a new function, the onDraw function here. The onDraw function and the draw function are the same, you just use different colors. So here we'll say vacant instead of the piece color. And then I will update the down function. Now I can see the piece moving down as we want. Now I need to rearrange the code, so I will use another function called fill. So fill here gets as a parameter the color, and then here for our draw functions and undraw, I will say this dot fill. Draw uses the pieces color and undraw uses the vacant color. Now let's create the move right function. So I'll just copy the code. Here, instead of incrementing the y position, we have to increment the x position. The same here for the left. We have to decrement this time the x position. Now for the rotate function, we have to increment the this.Tetromino number, so we have to say this.Tetromino number plus 1 modulo this.Tetromino that length. This is like saying 0 plus 1 modulo 4. This will return 1. Then we have to update our active Tetromino. Now let's go and control the piece. So we have to add an event listener to our document, which is keyed down. Whenever we press a key, we will fire up the control function. The function control gets event as a parameter. Then we'll use f statements. So f event.keycode is 37, means the left arrow, as f. I'll just copy this one more time. Now 38, 39 and 40. So if it's 37, we move down the piece, we move left the piece. If it's 38, we rotate the piece. If it's 39, we move right the piece. Then if it's 40, we move down the piece. Let's go and try that in our browser. So things are working fine. The problem here is whenever I move the piece or rotate it, it goes down automatically. So we have to set drop start to date.now every time we take an action. So now, as I move left or right, the piece won't go down automatically or when I rotate it. Now we have to detect the collisions. So we need a function called collision. So the collision function piece.prototype.collision equals function. The parameters are x, y, and the piece. We need to use a for loop, so to loop over all the Tetromino squares. So here we change this to piece.length. Now we need to check if the square is vacant or empty. If it's empty, we skip it. So if the square is not, so here we say if the square is not occupied, we continue and we skip it, so we go to the next square. Now we have to get the coordinates of the piece after the movement. we'll say let new x equals and the new y equals. So this that x plus c and this that y plus r are the coordinates of any square, plus x is the coordinate of the new square after the movement. Now we have to add our conditions, so we'll say f new x is less than 0, or new x is greater than or equal to the number of columns, or the new y is greater than or equal to the number of rows. Then we should return true, and then f the new y is less than 0, we have to skip it because this will crash the game, as there is no board with index -1, for example. So f new y is less than 0. We continue the loop. Then we have to check if there is a locked piece on the board. So we say f the board with index new y and new x is not vacant here. It is not vacant. Now let's go and update our movement functions. So for the move down, we'll say f there is no collision. Then we do the movement. Else we'll do other things like lock in the piece and generate a new piece. I will copy this for the other movements. So the same thing here. I will say if there is no collision, then we do the movement. I'll copy this for the move left, and then for the rotate is the same. Now let's go and give the arguments. So here 0, 1, this dot active Tetromino. For the move right, it's 1, 0, and the 1 for the x. Here 0 and -1 for the x. And here we should say 0, 0 as the piece rotate in its place, and next pattern. And here we declare or define our next pattern, so equals to this dot Tetromino with index. So here the code we increment the Tetromino number. Let's now check that. So here we can't go beyond the walls, but when I rotate it next to the walls, it won't rotate. So here is we need to use the kick wall. We need to declare a new variable kick equals 0. Now we need to know in which side the collision happened. So we'll say f this dot x is greater than column divided by 2. So here it's the right wall that caused the collision, and here it's the left wall. If it's the right wall, we have to kick the piece to the left, so we'll say kick equals -1. And the opposite, here we have to move the piece to the right, and then we check if there is a collision after the kick. If it's not, then we kick the piece. Now this must work, as you can see here. Now when our piece reaches the bottom, we have to generate a new one and lock it to the board. So let's go here and create the random function. So random piece, it will generate a random number. We'll say math.floor, math.random times the pieces that length. This should return numbers between 0 and 6. Then we will return this code. So instead of 0, we will use the random number. And here we will just say let p equal random piece. Now if I refresh, I will get a different piece every time. I have to go and update the movement function, the move down function. So here I will say p equal random piece. Let's go and try that. So every time a piece reaches the bottom, a new one is generated. Now we have a problem here. So the pieces go through each other because we didn't lock the piece. So now we have to create the function lock. So I'll say piece.prototype lock. So our function here, we must go and loop over all the Tetromino squares. So here we need to skip the vacant squares. So we don't want to lock the squares, the vacant one, to the board. Then we will check if the piece must or have to be locked at the top of the board, which is a game over. So we'll say if this.y plus r is less than 0. Then we alert game over to the user and then break from the loop. We also need to stop the animation frame, the request animation frame. So we need to set game over to true. Now let's go and update our drop function. Let's first declare our variable and set it to false, and here we will say if it's not game over, then request animation frame. Now we need to change our board's color, so that's how we lock the piece. So we'll say board with this.y plus r and this.x plus c, the coordinates of the piece, equals this.color. Then we have to update the move down, the last update. Now this should work, as you can see here, and this is a game over. Now everything's working. The last thing here is when we have a full row, we must eliminate it. How? We will do that by just moving the rows down. The code must be inside the lock function. So to move or to remove the full rows, we need to use for loop to loop over all the rows of the board. Then we need to set a new variable, is row full, and set it to true. Then we use a for loop to loop over the columns. And then we'll say is row full equals as row full, and the board with RC, with index RC, is not vacant. Now if the row is full, we have to move all the rows above it down. So we will say full starting from that row until y is greater than 1. and we increment the y. Then we'll use a for loop to loop over the column. Then I will say board. So board with index y, and c equals board with the 1 above it, y minus 1. Now the above, or the top one, the top row, so board with index 0 has no row above it. So we have to create it again. So we'll say board with index 0 equals vacant. We set all the squares the white color. Then we need to increment the score. By 10. Now let's go and declare the score variable. And after we remove the rows, we have to update the board by drawing it again. So this must work now. Now let's go and add an element so we can show the score for the player. We'll give it an ID score and set it to 0. We'll add some styling. So we have to align the blocks, and then we will change the font size, the font weight, so everything will look great. So I'll say font weight is bold, and then the font style or font family, so I will say monospace, for example. So that's good. Now let's go and add a line to update the score. I have to select the element first, so I'll say const score element equals document dot get element by ID of score. So we used score, yes. Now I will go and say score.element.inner HTML equals score. Let's now check if the score will increment. So here I will try to make a full row. Yes, so the score, so everything is working fine. So guys, thank you for watching. Enjoy playing the Tetris game you just made. Don't forget to subscribe, and see you in another video.